to get the best plasmonic structure or plasmonic structure for random lacing. So we did FTTD simulations where we actually generated randomly oriented particles or nanowires, and we looked at the electric field. So first we looked at the electric field in enhancement with change in aspect ratio. So we changed the length of the nanowires and looked at the electric field enhancement. And as you can see from this figure, you can see that the electric field is actually enhanced much better for smaller aspect ratios. So that means shorter wires will actually give you much better enhanced electric fields. So this is one criteria that you want to have. The other criteria is actually to have better scattering cross-section. So we looked at the scattering cross-section, and these two lines here are the scattering cross-section. So you see two opposite trends. The field enhancement is much bigger for shorter nanorods, but the scattering cross-section is much more bigger for longer nanorods. So there is actually an optimum, and we define the optimal parameter as the product of normalized electric field enhancement and normalized scattering cross-section. And you can see that there is a clear trend in this range where you can actually get the optimized effect for plasmonic random lacing. So this, what it means is that your aspect ratio should be between 8.6 to 57.7. If you have nanorods of this range, this is where you can get the best plasmonic random emission. And this is what we did. We fabricated silver nanowires or the silver nanorods, which have an aspect ratio between 10 to 17, which falls well within the optimized range. And we use this for together with rhodamine 60. So we took rhodamine 60 and put these nanoscatterers in there and pumped the this solution with a nanosecond laser, and this generates random laser from this particular sample. Okay, so this is the actual picture of the sample being pumped by 539 nanometer nanosecond laser. And what you can see is, so here the black curve is the fluorescence emission from rhodamine 60 without any random lacing. But when you keep on increasing the pump intensity, what you see is that the spectrum becomes narrower and narrower, and the intensity becomes much higher. So this black curve is actually multiplied by 10 power 4. So to make it easier to compare. Okay, so the black line is actually much lower than these other lines that you actually see. So we can actually get much better plasmonic random lasers. And one aspect that you can look at is the intensity. So if you pump with low energies, so there is no random lacing. So it usually increases gradually. But when you reach the threshold, the output intensity is much higher. So the slope actually changes, which is an indication of random lacing happening. You can also look at it from the full width at half maximum, or the line width of the emission. So if you look at the line width, the line width is much higher, about 50 nanometers, when you are below the threshold. And once you reach the threshold, the line width falls to very low values like 5 nanometers. Okay? So that is the kind of line width that you will have from such a random laser. So these are the properties that we got for our random laser. And we looked at the spatial coherence of the random laser. So if you take the conventional laser and do a Young's double slit experiment, you can actually see very clearly defined fringe patterns. So this shows that there is a high spatial coherence for a conventional laser. Whereas if you use a random laser, you cannot get any fringe pattern. So this means the spatial coherence is much reduced. We can also look at speckle contrast ratio. So if you use a conventional laser, the speckle contrast is, there is a lot of speckle, and the speckle contrast ratio is actually very high, 0.57. Whereas with a random laser, the speckle contrast ratio is much lower. So this means that the plasmonic random laser that we have will be very good for imaging applications. So we used wide field microscope imaging technique for fluorescence imaging of biosamples using such random lasers. So this shows the experimental schematic. I'll briefly go through this. So you have the pump laser, which is the conventional laser, and the random lasing media is here. So you pump the random lasing media with the pump laser, which creates the random laser, and you use this random laser to excite your sample, which is over here. So this can operate in two ways. One is the epi-illumination mode, which is the reflection imaging mode. So if you take out this mirror, the light goes directly to the dichroic mirror and goes through the microscope objective to the sample, and then you can image the sample using your camera. The other is trans-illumination mode, where you can actually put a mirror in here and illuminate the sample from the backside. So these two are two different geometries. So for thin samples, you usually prefer the trans-illumination geometry. For thick samples, you usually prefer the reflection geometry. Yeah, so we use different laser sources to see what is the improvement that we have. So we used bandwidth limited broadband LED that is shown in the blue here, a conventional laser which is shown in black here, and the random laser which is shown in the red here. So this is the emission spectrum of the three sources that we used. We can look at the image quality in different ways. We can look at first the resolution. So the resolution we looked at using standard Siemens chart. So this is standard test charts, prefabricated targets with spoke sizes. Here it should be around 500 nanometers. Okay. So if you can see these spokes clearly, that means that you have high resolution. So this was with the LED. This is not fluorescence imaging. This is normal imaging. So this is with the LED. You can actually see the spokes clearly here until the edge. So it has very high resolution. But when you look at with a conventional laser, because of coherent artifacts, you actually see artifacts happening here. So this is called a ringing artifact. So this is basically due to the coherent artifacts from conventional laser. But when you use a random laser, you actually get very similar images that is equivalent to using a conventional source or an LED source. So the lateral resolution of our system was found to be 454 nanometers. So the microscope that we developed can actually give you a resolution of 454 nanometers. The second thing that we can look at is the image content. So how truthful is the image to the original image? So this is why we started the whole thing about. Because if you use conventional lasers, you have coherent artifacts which will actually modify your image. So how truthful is your image to the original image? This can be found out using a correlation coefficient with the standard original image using this equation. And we did it for all three of these images. And we found that the correlation that with the broadband is about 0.81. With conventional laser, it's only 0.65, whereas with random laser, you get actually 0.83. So this will give you much truthful image of your sample that you are trying to measure or trying to image. So this is further analyzing the images that you get, and we can. So the next we went into imaging the actual biomedical samples. So one of these is that we looked at is human embryonic kidney. So these cells were stained with fluorescent markers, and we imaged them using 3 different techniques. So this is actually fluorescence imaging. So if you use LEDs, it has a broad emission, and this actually will give you much reduced fluorescence because it's not really optimized, or it's not really optimal for fluorescence imaging. When you use conventional lasers, you actually get much brighter images. But if you use random laser, you actually get much more better images. And you can actually see that when you use conventional lasers, some features here are missing. This is because you have coherent artifacts at those points, and this leads to non-uniform illumination of your sample. So the random laser here gives you much better images. And if you look at the contrast, with the LED, you get about contrast about 0.58. With conventional laser, you get about 0.81, and with random laser, you get much better contrast at 0.87. So the reason for this is that LED have low photon degeneracy, which gives a broad emission spectrum, and thus less efficient fluorescence emissions from your samples. So this is an image which shows clearly it's a magnified view of this portion. So with conventional laser, you can actually see that there are some dark areas here, which doesn't show the structures that are present in there. But with random lasers, we can even see those areas very clearly. This is another technique where you can actually use conventional lasers, but you have to actually introduce speckles first and then average it out over 1,000 of images and get back the same kind of images that you get from conventional lasers. So the point that I'm trying to make here is this is not, so you actually see these two structures are very similar, but this technique actually needs you to take 1,000 images, whereas you can get with random laser, just with one image, the same information that you have in the whole structure. You can actually see the difference between conventional laser and the random laser image. It's the same image, but with two different sources. We also did this for mouse kidney section, which is actually much more diffusive. And here, the difference is much more clearer. With LED, you have a very low contrast image, but with conventional lasers, you have still brighter image, but with random laser, you actually have much better images with about 23% contrast enhancement over conventional lasers. So with this, I would like to conclude. We designed low threshold plasmonic random lasers using silver nanostructures with tuned aspect ratios. And we showed that such random lasers can be used for artifact-free wide field fluorescence bioimaging, which will give you superior contrast of about 23% over conventional lasers and with sub-micron resolution. So I would like to acknowledge Professor Murugesan, Professor C. Vijayan, Professor Balyash Villiers, or Professor C. Vijayan and Professor Balyash as are the collaborators for this particular project. Dr. Padmanabhan, Dr. Gayatri, NTU India Connect program. So this was a joint project between NTU and IIT Madras. Ministry of Education Singapore, call EDP A* for funding and call group members. So thank you very much.
Thank you, Dr. Sujant, for giving us an overview of the recent activities in plasmonic lasers and its applications. The session is open for a very short 1 or 2 questions. We are actually running a bit behind the schedule, but I encourage at least some discussion should be there. So anybody? Okay, so tell me, what is the actual potentiality of this technology creating, commercial products, and how soon we can expect some plasmonic lasers with such a small line width? And
the limiting factor still is the random lasing media. Usually, what you have is liquid media, and liquids usually are not really preferred when you have a commercial product. So we have to move to solid-state based random lasing approaches. There are certain developments in this area which looks quite promising, and with the advent of that, I believe the random lasing can really replace conventional sources that are used in commercial.
Okay, how many groups are working in this area currently?
Yes, we are also working in this area. We are looking at fibers with
worldwide. How many groups are working in this area for?
There are about 10 to 15 groups who are actively working in this area to enhance random lasers.
Okay, thank you. Any questions? Okay, I think if there are no further questions, I think Dr. Sujant is around for at least one more day. Yes. Chitra.
Hello. Okay. Sir, actually, how we can improve the efficiency by using a femtosecond laser, because we are waiting for the arrival of femtosecond laser in our lab. So how could you expect this same techniques which we can, the preparation of nanowires and the application using femtoseconds, how we can improvise?
With femtosecond lasers, you can actually get pulses that are of the order of femtosecond, random lacing of the order of femtosecond. But usually, there is an overlap, and the fluorescence usually will take some time. So if you have a femtosecond laser, the overlap between the fluorescence and the pumping may not be optimal. Usually, people use nanosecond lasers for these kinds of works, nanosecond and picosecond work. Femtosecond also is possible. I'm not saying that it's not possible, but it may not be, or these kinds of structures may not be the suitable ones. You have to actually invent or look out for new structures with ultra fast response that can give you better lasers.
One more question. Actually, what are the advantages which we can prepare this synthesis silver nanowires using these laser ablation techniques? Not laser ablation, this techniques than other, because we can also prepare nanowires in other techniques. So is there any comments on?
So for this, we actually use the polyol process. So it's a simple chemical process. You can actually use ablation or other kinds of processes as well. So our intention was not really to optimize the nanoroad preparation, but yeah, of course, I mean, you can actually do.
So you already mentioned the aspect ratio. That's why
yes, the aspect ratio. Yes. So here, since it's a synthesis, colloidal based synthesis, it's easy to tune the aspect ratio. So just by controlling how long you grow it, or the concentration, you can easily control the size. So that was our main intention of using chemical synthesis. Whereas if you're using CVD or other kinds of techniques, you have to really control the parameters to really get the short size.
Okay. Thank you very much.
Okay, thank you very much. I invite Dr. Subhash Sahu of Department of Physics, Assistant Professor, to come to the stage to hand over the memento to Dr. Sujant. Thank you, Sahu, for presenting, and thank you, Sujant, for a wonderful talk. Thank you very much. So we are moving on to the next talk of this plenary session, or the last talk of the 4 noon sessions, Nonlinear Optical Properties of Novel Materials, Fundamentals and Applications, Professor Reggie Phillip of Raman Research Institute, Bangalore.
I request Professor K.J. Thomas, HOD Department of Physics, to introduce the speaker.
Okay, a brief profile of Reggie Phillip. Reggie Phillip is currently a senior professor and head of the department, head of the Light and Matter Physics Department of Raman Research Institute. After obtaining PhD degree from CUSAT, Cochin, he worked as a postdoctoral research fellow at the University of Regensburg, Germany. Dr. Phillip's research interests include laser production plasmas, ultrafast spectroscopy, nanostructuring using ultrafast laser pulses, and nonlinear optical behavior of nanomaterials. He has been in the organizing committee of a number of national and international conferences and has held visiting scientist positions at the University of Massachusetts, Boston, and the University of Central Florida, Orlando. He has published more than 200 research articles in peer-reviewed international journals, holds 2 patents, and has co-authored 2 books in 2 book chapters. Dr. Phillip is a reviewer to several international journals from reputed publishers such as American Institute of Physics, American Chemical Society, Optical Society of America, Royal Society of Chemistry, Springer, and Elsevier. Over to Professor Reggie Phillip for the talk.
Good morning, everyone. I'm Reggie Phillip from the Raman Research Institute in Bangalore. And first of all, I would like to thank Professor Swapna for inviting me to give a talk here. And the title of my talk is Nonlinear Optical Properties of Novel Materials, Fundamentals and Applications. Next. How do I move? Oh, okay, it's here. Yeah, so the contents of this talk will be a very brief introduction to nonlinear optics, only 1 or 2 slides. Then about some novel materials like nanomaterials, 2D materials and perovskites, and some nonlinear optical experimental techniques, and then nonlinear optical applications of novel materials. So looking at the differences between linear optics and nonlinear optics, so we can see that in the case of linear optics, the optical properties of the materials, there's a refractive index, the absorption coefficient, these are independent of the light intensity. Then the principle of superposition is applicable. The frequency of light or the color is not altered by passage through a medium. And 2 beams of light have no effect on each other when passing through the same region in a medium. However, all these are different in the case of nonlinear optics. For instance, the refractive index and the absorption coefficient, speed of light, all that will depend on the light intensity in this case. Then the principle of superposition is not applicable, and the frequency of light can get altered, and photons do interact with each other when they travel through a nonlinear medium. So that's why we can have effects like optical parametric oscillation, for example, where you can generate more colors or more frequencies when you pass light through a nonlinear medium. We can generate very short laser pulses through mode locking, Q switching, etc. And then we can also have solitons where the expansion of a laser pulse in time is compensated by nonlinear phenomena like cell phase modulation. So the generic theoretical approach to look at nonlinear optical behavior is to look at the response of bound electrons in a dielectric to an applied electromagnetic field. In the linear regime, when we look at the induced polarization density, which is the electric dipole moment per unit volume, we can see that it is proportional to the applied field E, and this is written as P is equal to epsilon naught chi1 E, where in the case of electromagnetic radiation, E is the electric field contained in the electromagnetic radiation, and P is the induced polarization density. So chi1 is called the linear optical susceptibility. Now coming to the nonlinear perturbative regime, we can see that we can write down the induced polarization density as P nonlinear is equal to epsilon naught chi1 E plus chi2 E square plus chi3 E cube, like that. And here we can see that the polarization density is proportional to E square, E cube, etc. So the corresponding susceptibilities chi2, chi3, etc. are the nonlinear susceptibilities of the material. To give an example, to look at second order nonlinearities, if we consider a material through which 2 electromagnetic beams having electric fields E1 and E2 pass by, and they interact with each other. So if we look at the E square term here, because we look only at the second order term. So if you write E as proportional to E1 e to the power I omega t plus E1 star e to the power minus I omega t plus E2 e to the power I omega 2t plus E2 star e to the power minus I omega 2t. So what it means is we have 2 beams with one of them having the angular frequency omega 1, the other one with angular frequency omega 2, which means 2 different colors. So when you calculate E square, this gives us many effects like second harmonic generation, sum frequency generation, difference frequency generation, DC rectification, etc. So all these are nonlinear optical phenomena. And I'm not going into the third order properties, which we will see a little later. as we go to the applications of these materials in NLO. So let us look at the important materials in which we see nonlinear optical phenomena. So historically, the very early materials which were studied for NLO were organic molecules. So after that, when nanomaterials came, people started off with metal and semiconductor nanoparticles. So here we can see that if we start with a single atom of any material, so here it is given for a metal. So when you start with a single atom, we have very discrete energy levels for the system. But when we increase the number of atoms, for example, this is a metal cluster which has a certain number of atoms in that, like for example, 10 atoms, 50 atoms, 100 atoms, like that. Then you have more energy levels coming into the picture, and it is like a molecular orbital system here in this case. But when you come to a nanoparticle which contains even more number of atoms, this becomes more or less like a band. But even then, there are discrete levels there. So looking here, for the metal, we see that when it's in bulk form, there are no discrete energy levels. These are bands. But when you go to the nanoparticle form, you see some band and some discrete levels. And at the atom, of course, like here. And in the case of the semiconductor, we can see there is a clear band gap, as we know. But again, when you go to the nanoparticle situation, you have energy levels here with bands, and atom again like very discrete levels. So that's what we see here in this picture for the semiconductor system. So this is why if you take gold nanoparticles of any noble metal nanoparticle of different sizes, then we will see that they have different colors. So this is one of our earliest works. Actually, this was published in year 2000. We worked in the picosecond optical nonlinearity of metal nanoparticles, gold, silver, and gold-silver alloy nanoparticles in this work. And to the best of our belief, this is the first paper where in a Cscan experiment, we found that this is not exactly like the Cscan, which is shown here, is not exactly like what was shown in the original Cscan paper by Sheikh Bahai in 1990. So here we could see humps which flank the valley, and we explained this in terms of the plasmon band bleach in the metal nanoparticles, and which turned out to be correct eventually. And later on, we expanded this work after many years in 2012, again working with gold atomic clusters. Here the difference is that earlier we were working with materials of a larger diameter, much bigger metal nanoparticles, but here we are working with real clusters with AU25, AU38, AU144, like that. So now we are much more into the molecular domain. One can call these like metal molecules. I mean, there is no such nomenclature, but this is what more or less it is. And then we could see that if you look at the nonlinear transmission through these materials, then the smallest clusters actually behave very much like very good optical limiters. But when you go to the higher clusters, when the size increases, the behavior completely changes. And at AU144, you can, this is AU144. And when you go to the plasmonic nanoparticle of 4 nanometer size, you can see that the nonlinear transmission increases for a certain intensity range and then decreases after that. So a lot of people worked in metal nanoparticles and semiconductor quantum dots in those days, and I'm not really going any further into that because of a limited time. So now we will look at 2D materials, which are very much being investigated these days. And graphene, of course, all that started with graphene, and these are called 2D layered materials. Graphene was rediscovered and isolated in 2004 in the University of Manchester. And the unique and remarkable properties of this 2D form of graphite have sparked rapidly growing research interest in the physics and applications of this 2D material. And the way it impacted nonlinear optics is in the following way. By and large, with very few exceptions, for example, surface second harmonic generation, nonlinear optics has been traditionally concerned with nonlinear optical interactions that take place in three-dimensional bulk optical media. So having found a 2D material, I mean, this opened up a lot of possibilities for nonlinear optical studies. Of course, in many, many areas, a lot of studies, very new studies, very novel studies happened. And naturally, in nonlinear optics also, we had a lot of studies happening. So looking at graphene, why it is interesting from an optical point of view is because it exhibits broadband absorption at optical and terahertz frequencies because of its nearly zero energy band gap. I mean, graphene practically doesn't have an energy band gap. However, it absorbs only about 2.3% of the incident light because it's just one layer, or sometimes you have a few layer graphene, but even then it's extremely thin. So it absorbs only about this much light, and everything else is getting transmitted. So one can say that it barely interacts with electromagnetic waves. However, the zero band gap, unusually large chemical and electrical tunability, and effects such as polyblocking provide unique functionalities for graphene-based photonic nano devices. For example, graphene exhibits saturable absorption, which plays an important role in laser applications, as we will see soon. And the large NLO response, ultra-fast dynamics, and high chemical and mechanical stability, and thermal and optical damage threshold, these are high. So all these good properties make graphene an excellent material for NLO studies. So this is the energy level description for various NLO processes in graphene. So we have the bands here, and this is an absorption which happens in graphene. And when an absorption happens, there are intra-band relaxations happening up here in the upper band. And then you have the interband transition to the lower band. And again, there are intra-band relaxation occurring here. Another point to note is that when you start exciting graphene, we have something called polyblocking, which means as you start populating the upper band, it becomes more and more difficult for pumping. So in such a situation, what becomes more prominent is two-photon absorption. So as you can see here, if the input intensity is high enough, then two photons will get absorbed together so that from a lower ground state, the system can go to a higher state up here. And it is also possible to have second harmonic generation, third harmonic generation, etc. in graphene. There are also other materials, two-dimensional layered materials other than graphene, like transition metal chalcogenides, black phosphorus, hexagonal boron nitride, perovskites, topological insulators, and all that. We also have hybrid structures containing 2D materials such as composites with dyes, plasmonic particles, 2D crystals, silicon integrated structures, all that. TCMs are semiconductor materials with formulas of MX2, and examples are MOS2, MOSE2, WS2, WSE2, TS2, and all that. So we have two kinds. One is transition metal dichalcogenides, and the other one is transition metal monochalcogenides. Here, M represents the transition metal, and X is the chalcogenide element. And they exhibit the typical layer-dependent tunable band gap. That is the advantage. Depending on the number of layers, the band gap can be tuned. And this can be tuned from 1 eV to 3 eV. This is the structure and spectral domain of applications of 2D LMs. So when we look at graphene, we can see that the absorption mostly happens in the, it starts from the microwave region itself, microwave, terahertz, far infrared, near infrared, far infrared, mid infrared, near infrared, visible UV. So in the case of BP, this is a little shifted out here. It mostly happens from the far infrared region. And for other TMCs, this is like in this region. You can see that the band gap is increasing. So here, in the case of graphene, the band gap is almost 0. But as you come here, it is like about 6 electron volts. The advantages of 2D materials are like for these reasons: large and ultra-fast nonlinear optical response, broadband and tunable optical absorption, ultra-fast recovery time, large optical and thermal damage threshold, high chemical and mechanical stability, low fabrication cost. So some of these are qualities which could not be obtained in other kind of bulk materials. So this is the reason why 2D materials are actually important for nonlinear optical applications. We also need to look at the symmetry considerations. For example, the crystal lattices of graphene and TMDC, they belong to different space symmetry groups. So the graphene lattice belongs to a D6H point group, which makes it a centrosymmetric material. And we know that when some material is centrosymmetric, it is not possible to have second order nonlinearity. So the lowest order nonlinearity in graphene is therefore third harmonic generation. In contrast, the TMDC monolayers, they belong to the D3H point group, which is non-centrosymmetric, and therefore, in this case, second harmonic generation can be the lowest order nonlinear optical process. So we can calculate the linear optical properties of 2D materials. Here, what is on the x-axis, we have the wavelength, and on the y-axis, we have the conductance. And the conductance of these materials is in fact related to the nonlinear, the refractive index through this equation where n is the refractive index. And here, the same calculation is done for certain other materials, 2D materials. And here, the calculation is done for the nonlinear constants. So we have the third order surface conductivity of graphene in this picture for a large range of wavelengths. And here we have the same calculation for certain other 2D materials. And for comparison, the value of gallium arsenide is given in this picture. Here, what is shown is the second order nonlinear susceptibility. Now coming to perovskites. So this is a perovskite is a naturally occurring mineral of calcium titanate with this formula CaTiO3. But its name is also applied to the class of compounds which have the same type of crystal structure as this. So this is called the perovskite structure. So we have many materials of this kind, and this is how some of the perovskites look. So people have found that there are a lot of emergent properties and applications for halide perovskites. So this is the same picture rotated by 180 degrees. So we can read many things here: sub-band gap photodetectors, upconversion photoluminescence, self-powered photodetectors, optical limiting, all optical modulation. So many applications for these materials are envisaged. Now coming to the experiments and applications. There are different experimental techniques in nonlinear optics, and these have been developed to characterize specific nonlinear optical properties of photonic materials. For example, we have harmonic generation, various types of Cscan techniques, four-wave mixing, pump probe studies, two-photon-induced fluorescence, self-phase modulation, etc. So in the harmonic generation experiment, so this is the experimental setup here. Basically, you have a laser and the beam then falls on your sample. So these are 2D materials. So basically they are flat, and it can be focused onto the sample. And when the harmonic is generated, this is like if you excite with 1000 nanometer, then the second harmonic will come at 500 nanometers at half the wavelength or double the frequency. So then that can be collected using this microscope and then taken to a photomultiplier tube, and then it can be recorded. So the theoretical calculation for harmonic generation in these materials, this for graphene, is given like this. And some experiments have actually shown that the theoretical calculation is reasonably valid. Here, in this case, you can see a band of second harmonic generation happening here, and another band of third harmonic generation happening here. And this is a measurement where multiple layers of graphene have been used. And when you have multi-layer graphene, your third harmonic generation output is more efficient. I mean, there is more output from that. Then another aspect is high harmonic generation, which is actually one way in which one can make extremely short laser pulses like attosecond laser pulses. So MOS2 has been used for this in one study, which appeared in 2017. And we see that high harmonic generation is possible in MOS2. Then Cscan is another experiment where we can look at saturable absorption and reverse saturable absorption in these materials. So different materials have shown either saturable absorption or reverse saturable absorption or some behavior in between. So these all have been investigated. So this is one of our works, recent works, where we studied something called hematine nanoflakes. So this is obtained by, this is hematite, and you have to ultrasonicate and then centrifuge. Then this is one way of getting the 2D material like exfoliation, which was done in the case of graphene. And we found that again, these are very good optical limiters. Now, using the saturable absorption property of the material, it is possible to make ultra-fast laser pulses. So in this experiment, an erbium-doped fiber laser is Mott-locked, and you get a very short laser pulse. So the Mott-locking, which is the technique used for generating very short pulses, is now happening here by means of graphene. So graphene is used for Mott-locking. So you get these extremely short laser pulses, which are only a few femtoseconds, about less than 100 femtoseconds in width. And you can also tune it over various wavelengths, which are near the telecom wavelength. This is another halide perovskite based saturable absorber for Q switching and mode locking of lasers. Again, you can see that you have a sequence of laser pulses, and this is the autocorrelation of the laser pulse, and you see that this is something like less than 1 nanosecond, and the temporal stability of the laser also is very good. Optical power stabilization, pulse reshaping. So all these are possible by means of two-dimensional materials. So here we can see that the power instabilities here is controlled, and also the spatial profile has become more soft by applying this. Then optical limiting is something where you reduce the power of a laser beam when it passes through some materials. So these materials are called optical limiters. So we did a lot of work in optical limiting, and it is found that 2D materials are useful for optical limiting applications as well. And just in passing, I would like to mention this paper with Swapna when she was a PhD student many, many years back. We collaborated, and so Sandeep also is an author. And with Professor Anandaraman and myself, we are the other authors in this paper, where we showed for the first time that ferrofluids are excellent materials for optical limiting. And we actually also have a patent on this work. Then excitation dynamic studies, like pump probe kind of studies, can be used for looking at the excitation dynamics of materials. So here, the excitation dynamics in MOS2 has been studied by means of femtosecond laser pulses. All optical imaging and characterization of 2D crystals is possible by second harmonic generation in these materials. So this is an example of that. Then we can also have electro-optic modulators. So in this particular work, we have a laser beam which is polarized to start with, and then there is a λ/4 plate which actually makes the beam birefringent. It makes it circularly polarized. But when you introduce the 2D material in here, that also introduces another λ/4 phase change, so that in effect it becomes a plane polarized beam again. And that plane polarization can be investigated by means of the analyzer, which is here. So we can use 2D materials as very good electro-optic modulators. Then multi-photon pumped up 2 minutes. Up conversion, micro and nano lasers. We can make lasers out of these things. So I think all optical modulation also is possible. I'm not really going into all those. In 2 slides, I will finish. So we have worked in nonlinear optics over the last 22 years, I should say, after I joined Raman Research Institute, and several collaborators in metal nanoparticles, semiconductors, quantum dots, organics, polymers, nanophosphates, ferrites, oxides. Here, Swapna has collaborated. Then graphene, 2D materials, and all that. So students, Sandeep is here. Then many of them have worked. And with this, I will stop. So this paper is very special. If you look at the authors here, what is important about this paper is that all these authors are speakers in this conference. Thank you very much.
Thank you, Professor Reggie John, for overview of these aspects on nonlinear optical properties of materials. Discussion and questions, please. So, so can you just explain to us or tell us about the difference between these nonlinear optical properties in these 2D materials versus the characteristic, in the old times, 3D materials also you have these nonlinear optical properties that have been investigated.
Yeah.
And what is the difference and what is the advantage of
the major advantage is that the coefficients are, first of all, very large. So the nonlinear optical effect is much larger. So even with a very thin material, with very small size and all that, we can have a large effect. And that is because it can be calculated, because from the sheet conductance of graphene and all that, it can be calculated that even with very small absorption, the nonlinearity is much higher. So therefore, it is possible for us to introduce these materials into photonic components. For example, where I showed Mott locking, these are erbium doped fiber amplifier. You can make femtosecond pulses out of it by using an extremely thin graphene sheet in the optical circuit. So, but if you want to use the bulk material for this, it is much bigger. And then, you cannot really integrate this into a very small photonic nano device, for instance. And also there are other things like broadband response, then a number of advantages compared to 3D materials are there.
Yeah, but then how do you scale the intensity for these materials? You might need, you mean for applications, you may need to we need a power, a higher power.
Actually, not too much. Not too much. So that is the advantage. Like, an erbium doped fiber amplifier, it doesn't give you lots of power, but even that laser can be mod locked by means of a saturable absorber, which is made from a 2D material like MOS2, for example. So the thing is, the intensity that you need in this particular case is much lower than the intensity that you need in the case of a normal, typical 3D material. Yes.
Okay, any more questions on this topic? If not, let me thank all the speakers of the morning session for wonderful presentations. And that ends the session, the plenary session now. And after this, there's a lunch break for 45 minutes. And then we move on to the afternoon session with parallel sessions. There are 2 parallel sessions. I think there is only one parallel session. There are two other parallel sessions. Okay, so now I invite Professor Shaktivel, head of the department biochemistry, to come on stage to present a memento to Professor Reggie Phillip. I said chemistry, didn't I? Sorry, head of the department of chemistry. Thank you, Professor Shaktivel, and thank you, Professor Reggie John, for the sessions. Thank you very much. So we see exactly after 45 minutes. So please come forward, come afterwards. There is a lunch.
We will resume the event with 3 parallel sessions in the afternoon. Kindly note that parallel session 2 for short invited talks SI1 to SI12 and parallel session 3 for oral presentations O1 to O18 will be taking place in Narmada building, which is the adjacent building to our current venue. Parallel session 1 will be taking place in Sabarmati Hall in Sabarmati building, which is the same venue we are in at the moment, with a lecture on non-collinear spin textures in soft ferromagnets by Dr. Sinoy Thomas, Assistant Professor, Cochin University of Science and Technology. I repeat, parallel session 2, short invited talk SI1 to SI12 and parallel session 3, oral presentations O1 to O18 will be taking place in Narmada building, which is the adjacent building to the current venue. And parallel session 1 will be conducted in Sabarmati Hall in Sabarmati building. Lunch is arranged in Narmada building. Please make sure to take your food coupons with you, which is already provided in your conference bag. Kindly be back after 45 minutes.
Hello. Hello, testing. Hello. 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 Hello, testing. Hello. 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 Hello, testing. Hello. 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 Hello, chick. Hello. 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 Hello, testing. Hello. 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 Hello, chick. Hello. 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 Hello, chick. Hello. 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 Hello.